Right, so we have extracted patches from images, but there's a huge number of them. So you can see that we have 156,000 patches. We don't want so many. So we'll be making do with 40,000 patches that we'll be dividing up into train, test and validation sets. But the idea is to get these 40,000 patches randomly from this big set of 150,000. That is, we shouldn't get concentrated on a particular image, or we shouldn't have patches that are very nearby to each other in their original image. So the way to do that is to use the numpy random dot permutation function. So we define random idx is equal to np dot random dot permutation and patches. You can see what this does. So random idx is just all the indices from 0 to n patches minus 1 arranged in a random order. You can see the max value of it here and the min. Right, so it contains all these indices in a random order. And let's define n samples as 40,000, the number of patches that we want kept. Out of these 156,000 random IDXs, we'll keep n samples random IDXs, random IDX n samples, and we'll use this to define our kept patches. OLS underscore patches kept IDX. Run this. Now that we have extracted the limited number of patches that we are going to use, we like to process their values to be in some desirable ranges. One desirable property for these values to have is to be of zero mean and of a fixed variance. This is just standard practice. So for this, we'll be using the sklearn preprocessing module. So we can run this. Preprocessing has a class called standard scaler which will do these things for us. So let's define an object of that class, processing dot standard scaler. This goes into our scalar object, but we'd also like certain settings here. We'll make copy equal to false so that standard scaler works on the memory provided by the input data and doesn't make a copy of it. And I like the standard deviation of the output data to be 0.33. Why I do that, I'll explain shortly. So we have a scalar object created. Let us transform our patches using this fit underscore transform kept patches. Right, so process patches is going to be the scaled version of our original patches. Let's run this, and we have the output in processed patches. Now assume that the values in process patches were being generated from a Gaussian distribution. That is, each pixel was being sampled from the same Gaussian distribution independently. In that case, you would expect more than 99% of the values to lie between plus and minus 3 standard deviations of that random distribution. That is, because our standard deviation is 0.33 here, we'll expect more than 99% of the pixels in process patches to be between -1 and 1. So in that case, now another desirable property that I'll want is that I'll want the data to be in a fixed range of, let's say, -1 to 1. So if I truncate, if I saturate all the values that are breaching this range, that is saturate everything above 1 to 1 and everything below -1 to -1, that will obviously upset the Gaussian shape of the histogram. For one thing, it will truncate the histogram outside of a -1 to 1 range, and it will distort the histogram within that. But the useful thing here is, if I am keeping all the values between -3 and +3 standard deviations, I won't be upsetting the shape of the histogram much. And that is the reasoning that I applied when I kept the standard deviation as 0.33. Now it'll make it easier for me to keep the data in a fixed range of -1 to 1. So let's do that. Process patches of process patches greater than 1 should be equal to 1, and smaller than -1 should be equal to -1. So that has brought my data into a fixed range. But an autoencoder learns to reconstruct data. That is, it checks its reconstructions versus the data that has been provided at the input to make the gradients for the learning. In that sense, suppose you are using sigmoid units for an autoencoder, which is a standard methodology, you will not be able to have negative reconstructions. Right now our data is lying between -1 to 1, so that is a problem for us. We'll need to shift this into a more apt range for usage with sigmoid output units. Now another fact to consider is that when using sigmoid hidden units, it's good to have the input data in a range of 0.1 to 0.9. This is presented in Jan LeCun's efficient backpropagation paper. So considering these two factors, having positive data and having it in a zero point 0.1 to 0.9 range, according to two different constraints, the first one of positive data is coming from the sigmoid output units, and the second one of a zero point 0.1 to 0.9 range is coming from sigmoid hidden units. So we'll be combining these two constraints and making our data to fall between a 0.1 to a 0.9 range. So let's do that. So processed patches should be equal to processed patches plus 1. So this makes everything lie between 0 and 2. We multiply this by 0.4 so that everything lies between 0 and 0.8, and now we add 0.1 to it, so the minimum value shifts up to 0.1 and the maximum goes till 0.9, which is what we wanted. After running this, we have completed our pre-processing of the data. Now the next step, so let us put proper comments here. Pre-processing the data. The next step ought to be to divide the training, validation and test sets. Division of train, valid and test sets. For this purpose, we'll be using the sklearn cross-validation submodule. So let's import that. Now cross-validation has a function called train test split. It does what its name says. You give it some data and you tell it what the size of the test set should be, and it will give you a train and a test set. So because we want 3 sets, we'll do it in this way. Train underscore and valid and test underscore should be equal to cross validation dot train test split. Processed patches test size should be 0.3. We want to use 70% of the data for training, and we'll also put in a random state argument here so that we can reproduce our results. We'll get the same splits every time, right? So this finalizes our train set. Let's now separate the valid and the test sets. Actually, you don't need to do this. Valid is equal to, but let's just do it in this way. Cross validation dot train test split valid underscore test underscore test size equal to 0.5 random state equal to 0. 0 is just some value you can always remember. Right. So now we have divided our patches into train, valid and test sets. You can see their sizes here. 28,000, which is 70% of 40,000. Valid ought to be 6,000. And test is also 6,000. So with this we have also divided our data into train, valid and test sets. The next step is to dive into Theano and define our model and start working on the GPU.